Hello everyone, so today we're going to have a look at things called harmonics and how they behave in strings and pipes. So before we go on to what a harmonic is, first of all let's just recap the term natural frequency. Now the natural frequency of a body is the lowest frequency standing wave that can be created in the body. So for example, in a piece of string, the lowest frequency standing wave that has the same amplitude at each point will be a single antinode like this. So the wave will go from this position to this position and back and forth like this. Each individual point along that string will have the same amplitude at all times. So at either end on the nodes, we're going to have zero amplitude, and in the middle we'd have a much larger amplitude, but it would be constant at each point. So now applying that idea to harmonics. A harmonic is a multiple of the natural frequency of the vibration of a body. So if we go back to looking at our example of a string, we said that this is our fundamental frequency or our natural frequency. So if this is 1 times our fundamental frequency, then this must be a harmonic, because 1 is a multiple of a number. If we're to double that frequency, we get 2 times the frequency. This would be called the second harmonic. What this would look like is the same length piece of string, but a wave that repeats itself twice as often. So you can see we're going from having a node to an antinode, back to a node and another antinode. So this would be our first harmonic. This would be our second harmonic. On a string, we always have a node at each end. So we can see that up here and down here. Here we can have a look at what all of the different harmonics would look like up to the 7th harmonic. So if we imagine a base frequency of 100 Hertz as the first harmonic, then the second harmonic would be 2 times that, 200 Hertz. The third harmonic would be 300 Hertz, and so on down to the 7th one, which would be 700 Hertz. What is important to see here as well is that, like we mentioned before, each time we have a node at either end of the string, and that the number of antinodes is the same as the amount of harmonics. So the first harmonic we have 1 antinode, the second harmonic we have 2 antinodes, third harmonic we have 3 antinodes, and so on. It's also specified on the course that you have to be able to relate the length of the string to the wavelength of each harmonic. For the first harmonic, this can be represented using the following formula. The length of the string is equal to the wavelength divided by 2, or half of the wavelength. This makes sense because a complete wave would go from a node back to another node and then end up completing another cycle like this, and then similarly the other side like that. So a full wavelength is the distance it takes the wave to complete its cycle, meaning that the length of the string here only represents half of the full wavelength. When we look at the second and third one, we might see a pattern starting to form. In the second one, the length of the string is exactly equal to 1 wavelength. For the sake of seeing our pattern a bit more clearly though, we can say that the length of the string is equal to 2 times the wavelength over 2, which does just simplify to the length being equal to the wavelength, because 2 divided by 2 cancels out. For the third harmonic, we can see that 1.5 wavelengths go into each length of string. Here we can see the wave repeats itself 1 time, then another half a time within that length of string. So we can say that the length is equal to 3 times the wavelength over 2. 3 over 2 being 1.5 wavelengths. Perhaps you might be seeing the pattern now. But for an open string, the wavelength times the harmonic number divided by 2 will give you the length. If you want to continue this pattern on down now, try and get down as far as the 7th harmonic and see what the relationship is between the length and the wavelength for the 7th harmonic. Pause the video until you're ready to carry on. So hopefully if you did that correctly, you would see the pattern and you'd recognize the length is going to be equal to 7 times the wavelength divided by 2. Again, as we've said, for a string, to get the relationship between the length and wavelength, you multiply their harmonic number by the wavelength and divide it by 2 to get the length. Now we'll have a look at pipes. Pipes are a little bit more complex than strings. The main thing to remember is that the closed end of a pipe will always have a node, and the open end of a pipe will always have an antinode. You can see this in each of the 3 examples here. The closed end has a node, and the open end has an antinode, or an area of maximum amplitude. So if we want to draw a diagram for the first harmonic, it will be the simplest or the longest wavelength that we can have that will have a node on one end and an antinode on the other end, which will end up looking like this. The way that I remember these for a pipe that's closed on one end is I remember first harmonic will have 1 node, the second harmonic will have 2 nodes, the third harmonic will have 3 nodes. And as we can see, as we go from left to right, from the first harmonic to second harmonic, third harmonic, the frequency increases each time and the wavelength gets smaller. If we look at the relationship between length and wavelength for these pipes that are open on one end, we'll see a similar pattern, but one that's a little bit different. So looking at the first one here, our first harmonic, what we'll see is that it only goes a quarter of the way towards completing a wavelength within that pipe. Because we would still have to travel from our node back to another node, which would be half a wavelength, then complete that cycle on the other side. So the distance covered here is only a quarter, then we have 2 quarters, then 3 quarters, then 4 quarters of the full wavelength. So we can say that for this one, the length is a quarter of the wavelength, or wavelength divided by 4. For the second one, we're 3/4 of the way towards completing a full wavelength, which you would see happen up here. We have a half, 3/4, and then finally a full wavelength. So we can say the length here is 3/4, and then for the final one, we have 1 full wavelength and another quarter wavelength. So we can say that we have 1 1/4 wavelengths inside in that length, or 5/4 of a wavelength. So again, the pattern we can see here is that we're increasing by an odd amount on the top and then making sure the number on the bottom is 4. So my task for you now is to try and come up with the formula that will give you the relationship between the length and the wavelength for the 5th harmonic. You can pause the video now and just press play again when you're ready. So the answer that we'll be looking for is going to have a fraction in it. We know that the length will be equal to not 1, not 3, not 5, not 7, but 9 for our 5th harmonic. So 9 times the wavelength divided by 4. This will give us the relationship between the length and the wavelength for the 5th harmonic. The last thing that we're going to look at now is a pipe that is open at both ends. So we looked at our previous pipes that had an opening on one end, but were closed on the other. we said that any open end would have an antinode, and any closed end would have a node. But when both ends are open, that means there's going to be an antinode at both ends. As far as the relationship between length of the pipe and the wavelength here, it's going to look very similar to a string, just that instead of having a node at each end, we have an antinode at each end, but the math's going to be quite similar. Looking at the first harmonic here, we can see that a half wavelength is completed on the length of the pipe. So a full wavelength would bring us back to about here, same point that we started at. So we can say for this one that the length is half of the wavelength, because again a full wavelength will be coming down to about here, so half that would bring us the length of the pipe. For the second one, if we follow it from one point here at the antinode, it completes one full wavelength, or like with the open string we'll say 2 wavelengths divided by 2. Again, this just means one wavelength, but allows us to see the pattern a bit more clearly. And then for the third one, if we follow it along, we see that we create one full wavelength and another half wavelength. So this will give us the length being equal to 1.5 wavelengths, or 3/2 wavelengths.